In our previous video, we talked about forces, constraints, and collisions. Actually, the idea of collision is involved in all three, and it works a little differently from our usual way of thinking about it. All the details are available if we enable the collisions attribute on our jit.phys.world and filter the dump outlet using root collisions. The result? A max dictionary, a complex type of message, is output for each render, and each dictionary contains a subdictionary for each collision, which we can post in the max window using dict.print. It seems collisions are happening all the time, even though there's nothing moving. What's up? Well, in our jit.phys world, the word collision refers to any contact between physical bodies. So it's often something more like a state of being in contact, rather than the moment of impact. In the dictionary, the duration tells us how long the two objects have been in contact. When the duration is 0, that's the moment of first contact. Gravity acts throughout the world, but you can also set up forces that act only in a specific area, like a force field. To do this, put a jit.phys.ghost in your world. The ghost has a collision shape and a force. Any bodies inside the collision shape are acted upon by the force. Here's a ghost on the right side of the world box, pushing strongly to the left. In this patch, we can turn gravity on and off, while conversely turning a force off and on. Note that when the object has a mass of 1 kilogram, gravity and this particular force seem to act identically. When we increase the mass, gravitational acceleration is not affected, but the acceleration caused by the force is decreased. Let's take a closer look at the idea of constraints. Here is a capsule-shaped grid shape and body floating and spinning freely. We attach a constraint object, jit.phys.6dof, and suddenly the body is attached to a single point in space. We can still point it in any direction, defined by the x, y, z axes, and we can still rotate it around any of those three axes, so we do have 6 degrees of freedom, even though it's tethered or constrained to one point in space. That point is the center of the constraint, so we sometimes just call it the constraint. The location of that point is set by the attribute position 2, and the distance from the center of the body to the constraint is set by position 1. So the constraint is like a rigid leash. Position 1 is the length of the leash, and position 2 is where it's attached. The 6 degrees of freedom determine how the attachment point can move. For each degree of freedom, there is a lower limit and an upper limit. So for 6 degrees, we have a total of 12 numbers to set. Note that the lower and upper limits for position are all 0, which means that the leash is firmly attached to the origin. Let's increase the upper limits and see how the body is allowed to move. It's still attached, but the point of attachment can move around. Now let's try the angular motion. By default, the upper limit is a negative number, thus smaller than the lower limit. That seems strange, but actually it's another special convention. It means that there are no limits. It can move completely freely. Setting the upper limit to 10 means that the object can move only between 0 and 10 degrees around the point of attachment. And setting the lower and upper limit to the same value locks that degree of freedom to a fixed value. Other constraint objects tend to have 1 or more degrees locked. For example, jit.phys.hinge locks all 3 positions and 2 angles. So it has only 1 angle and thus 1 upper angular limit and 1 lower angular limit. So for this object, the point of attachment, the constraint, is analogous to a hinge in real life. Things really get interesting when 2 bodies are connected by a constraint. You can use the 2 outlets to connect to the 2 bodies, or you can name each body and use the constraint's body 1 and body 2 attributes to refer to those names. Let's try this with our hinge. Now they move through space together. The position 2 attribute no longer determines the fixed location in space. It determines the position of the constraint relative to the center of body 2. With connected bodies, the other thing to note is that the collisions attribute is explicitly set to 1. So this is normally default behavior, and they bounce off each other as you would expect. Why the extra attribute? Let's turn it off. Aha, now they can overlap. Although this might seem strange, it can be useful if you're building an articulating arm and you want the hinge located inside the arm. Let's talk about frame rates. In Jitter, it's common to use a very fast Q metro to drive the patch at its maximum frame rate, a number that can fluctuate wildly. How does that affect moving jit.phys bodies? It's something you need to think about any time the frame rate goes below 60. That's the default frame rate of the physics simulation, which calculates the result of the bodies moving and interacting for 1/60th of a second. For that reason, we've been running our Q metro with the attribute interval set to 60 Hz. But what happens if the patch slows down to 10 frames per second? The ball slows down. The 1/60th of a second steps are happening only when the render bang happens, that is 10 times a second, and the physics world doesn't skip steps to stay in sync. In this case, you have to give the world permission to do more calculations per render bang, or more substeps per step. We set this with the max substeps attribute. Divide the physics frame rate, in other words, the attribute fixed time step, by your minimum Q metro frame rate and add 1. So 60 divided by 10 is 6, adding 1 makes 7. We set max substeps to 7, and now the ball falls at the right speed, even though the movement is jerky because of the low frame rate. Now we've seen some essential features of Max's physics objects. This opens up a whole new way of moving shapes in space, letting the shapes move by themselves.